How's it going, everyone? Welcome to the fifth drill of this semester. Today, we're going to be going over ANCOVA. I've already loaded the tidyverse here, so we're just going to get right into it today. The study that we're going to be considering is researchers are interested in comparing the effectiveness of 3 different software packages that are supposed to help students get better at math problem solving. So participants are randomly assigned to 1 of 3 programs that's supposed to help people get better at math, and then they're given a math problem solving test. Smartly, the researchers also believe that there's some pre-existing level of math ability before they're exposed to the program, and that ability is probably also related to the score of their math test. So they also included a measure of math ability. So that's the 3 variables that are in the data set that we're looking at today. The variable called IV is one of 3 packages that's numeric and needs to be, we'll factorize it. COV is our covariate, that's that measure of math ability. And then DV is the score on the standardized math problem solving test. So this week, just to give you a little bit more experience working with R's defaults, we're going to make a factorized version of the independent variable, and we're just going to use as factored to dummy code it. And so when we check our contrast, we can see that's exactly what we have, where that first group is the reference group by default. So we'll check our models. First thing that we're going to do is we're going to do it in 2 steps. And the reason that we're going to do it in 2 steps is first we're going to regress the dependent variable on just that covariate, so in other words, we're regressing their test on the math score, or their score on the math test, regressing that score on the measure of their pre-existing math ability. And then in step 2 model, we are regressing that on the same thing, but also our dummy coded factor variable IVF. So then when we do this ANOVA here, what we're looking at, and we see that this is a significant F here. So this is essentially looking at, if you compare, just like all the model comparisons that we've done before so far this year, we're basically comparing Model 2 to Model 1 and asking, is the reduction in error significant? Or, that change of R squared, is that significant? And the answer is yes, it is, which is, really not surprising that a model that has our primary independent variable in it predicts something better than just the covariate, although that is good to know, at least that, because then you could at least say, you could have somebody argue, well, if you just skip straight to step 2, then how do you know that this covariate isn't explaining all the thing, that your program is irrelevant? The only thing that matters is their pre-existing math ability. And by splitting this into 2-step model and doing that model comparison, you're able to see that yes, no, that is change in their math scores above and beyond their pre-existing abilities there. And so then when we look at the ANOVA for the full model, that's step 2, we can see right here that this is where we get we focus on this one particular line, because those covariates are just things that we are not interested in interpreting generally. Like, of course, people's pre-existing math abilities are going to be related to the score they get on some test, but that's not scientifically interesting to say. And so if we look at this as a summary, so looking at it as a linear model instead of as an ANOVA, we can get more information out of it, because recall that these are dummy coded. So what that means is that with the first group being coded as the reference group, right now, because we did not mean center our covariate yet, here's how we interpret this coefficient table from step 2. The group number 1, the first program, is predicted to have a standardized math score of 12.7 if they have, or controlling for specifically at the value of 0 for their pre-existing math ability. So again, because this is, as I've said all year, the intercept is the average when everything else in the model equals 0. So here, that means that when covariate equals 0, in other words, when that math ability, pre-existing math ability equals 0, and when the groups equal 0, which is that first group. So group 1 with a 0 pre-existing math ability would be expected to score 12.7 on this test that is our dependent variable. And then for each 1 point increase in pre-existing math ability, we would expect a 1.67 point increase in that standardized test for that group. But then down here, again, controlling for the pre-existing math ability at 0, the group number 2 is expected to be 2 points higher, or 0.2 points higher than this first group, or 12.9327 points on their dependent variable math test. And then the third group, again, controlling for a pre-existing math ability score of 0, is expected to be 7.5686 points lower than group 1 here with this 12.7. Now, it doesn't really make a lot of sense to talk about, or to think about, like, the covariate as being 0. So instead, if we center our covariate here just by subtracting the mean from it, and then we're going to fit the same model, but instead of using just cov, we're going to use cov.c that we created here, that centered covariate. And we're going to make step 2c. And now when we look at our coefficients here, it gives us a little bit more useful information. So now, instead of predicting that group 1 is going to have a score of 12, this looks a little more realistic. Now what we're saying, still everything that we're saying here in this model is controlling for the average pre-existing math ability, because we're now using that centered. So now when cov c equals 0, it's still, the intercept is still the predicted score when everything equals 0, but now cov c, 0 means the mean of pre-existing math ability rather than 0 pre-existing math ability. So now for somebody in group 1 with the average pre-existing math ability, we're expecting them to have a score of 70.39 or 3839. Then again, holding constant that average pre-existing math ability, we're expecting the people in group 2 to score 70.59, and then group 3 will be at 70.39 minus 7.56. Now, if I'll show you here. We've seen before this GGEM means, that's estimated marginal means, and if we just put in our model and tell it that our terms, we just want our main independent variable, you'll notice here that it says adjusted for cov 37 or 34.37. And if we look at what our mean of cov is, you'll see that it's 34.37. So in other words, GMEM mean or GGEM means automatically, if you leave out a predictor, it will automatically adjust for it and mean center it unless you tell it something specifically else to do. So in other words, these here, what you're getting here are the estimated, the adjusted means. And if we look back at our summary now, we can see that that first group, again, we said controlling for the average pre-existing math ability, statistically controlling for it, that is, that 70.39, and then we can see that average for the adjusted mean is 70.39. And then if we look at 70.39 minus 7.5, we'll call it 7, we get 68.82, which is what we get for that third group there. And then obviously 70.38 plus 0.2, we get 70.59 here. So again, this GGEM means, what it's telling you here is that this is the adjusted means for these various things. However, that's different from the actual means. So if we run group by our independent variable, the factor, and then compute the actual mean of the DV, we can see our adjusted means are 70.39, 70.59, and 62.82, whereas the actual means are 68.6, 68.8, and 66.4. So what this is missing is that information about the covariate, because these well, we'll come back to that here in just a second. And so first, let's look real quick at a couple plotting things. First, if we just used GM smooth like we have before, we would be able to see that this plot is actually wrong. And the reason that it's wrong is because you can clearly see that there's an interaction allowed here, that this red line crosses the green line. They're not all parallel. But with covariates don't interact. And so I mentioned earlier last year that the problem with this geom smooth is that it can only handle one predictor. It's y regressed on x, and if you get any more complicated than that, then geom smooth won't necessarily handle your regression lines properly. But so one quick way to plot this instead of using geom smooth is just to extract the predicted values or the fitted values. Those are synonymous terms. And extract those fitted values from your model and plot those with geom line instead of geom point. So this is kind of similar to what we've done with ggpredict, where we use ggpredict to get some predicted or fitted values, and then we plotted those. So here we're doing the same thing, that if we take this first part and then just add on this next line, where all we're doing is we're adding in geom line, and we're overwriting the y, because here in the global aesthetics of ggplot, we set our y to dv, x is covariate, or cove, and color is IVF. So since here in this geom line, it will get the x and color from these global. Remember that the global settings is like the aesthetics that you put here inside the ggplot parentheses. So we're overwriting that the y value and making it instead the fitted values from step 2, which if we just run that subset, we'll see that it just gives us the actual predicted values for each of those data points. So now that will be our y value, but the x will still be the same cove variable, and the color will still be the same IVF variable. So when we do those things together now, that's where we get these lines that it takes each of these fitted values and then connects a line to them appropriately depending on which IV group that they're in. Then if we wanted to add, say, the mean of the covariates here, we could say geom v line for vertical line and just tell it the x-intercept equals the mean of df cove. Then, Bill likes the theme BW. So if you wanted to add that on. And then finally, just one more piece that there's if you wanted to add on a function that will convert your colors to grayscales. So putting that all together, here's what your plot would look like. And now, as a reminder, look at the difference between that plot and the original one. This is with geom smooth. And this is when you manually extract the fitted values. And in fact, let me zoom in here a little bit, make it a little bigger, because it looks like there's just one line. But you can see that there's actually two lines here for groups 1 and 2. It's just that groups 1 and 2 are pretty close to one another. And group 3 is kind of separated from those. But in the geom smooth, when it's allowed to interact, you can see that that's where we get that crossing. So the last thing that we'll cover briefly is our equal slope assumption and our independence of the groups and the covariate. So as a reminder, what the equal slopes assumption are, that is asking, we are assuming that each of these, the slopes of these different lines are equal to one another. And so all we have to do to test this equal slopes assumption is include our interaction. If we include our interaction, which again, that's what geom smooth did here. If we include this interaction and test it and now see like, well, is that interaction significant? Because if it's not, then that tells us that the slope doesn't depend on which group it is in. If it is significant, then we'd be in some trouble here with this particular assumption, because that would say like if this red line was turned enough to make this interaction significant, then what that would tell us is that the slope of that group is different from the slope of the other two groups, and so we are not following that equal slopes assumption. So we fit that model, look at our ANCOVA, and we see that nope, that interaction is not significant. The that covariate is, which is unsurprising. Some people kind of crap on things whenever people include covariates and don't want to interpret it, because they say, well, how can you not interpret it? It's significant. Look at it. And my reply to that is, well, of course it's significant. That's literally why we included it. You include it in the model because you expect that it explains part of the variance, but it's unrelated to your predictor. And so, of course, you include it in the model, but and of course it significantly predicts it. If it didn't significantly predict it, it wouldn't make much sense to include it as a covariate. So that's one way to think of it, is just, of course your covariate is significant. Otherwise, why would you include it? Which isn't necessarily to say that you should remove a covariate just because it's not significant. Don't mince my words there. But either way, our interaction is not significant. And when we look at our summary, we can see that not only is that ANCOVA, the overall interaction, not significant, but looking at the interaction of that covariate with each of the two factor groups, the contrast codes or the dummy codes that we had in there, neither of those are significant. So we are in good shape there. And then the final thing that we test is the independence of the groups and the covariate. So all we're going to do here is we're regressing the covariate on the IV. So the way to think about this is like you're just asking if you can predict the covariate score based on sorry, that's backwards. If you can predict which group they are in, based on what their pre-existing scores were. Because nope, I had that right the first time. Disregard. Oy, it's been a day. Yeah, so our outcome is their covariate score, and we want to know, can we predict their covariate score based on which groups that they are, which would only be possible if there was some sort of systematic difference between if there was a failure of random assignment. And that's why this is usually not a problem in research psychology, because we often have random assignment, and so you might test this kind of thing just to make sure you didn't have a failure of random assignment, but you're not expecting this to be a problem, because if you randomly assign people to these three groups, then you would expect that the level of pre-existing math going into the groups would be also randomly assigned. So there'd be some people who are really good at math and some people who are really bad at math in like each of the three groups. And so if you regress your covariate on your factor and it is significant, then what that tells you is that there is some sort of systematic relationship between that covariate and one of your groups. And so that there's some overlap there. And so including it in the model may be sucking up some of that variance that your factor should be predicting. But when we look at it here, we can see that that is not the case. And so, again, this is just the kind of thing that, especially when you are doing random assignment, in my own research, it's often the case that when I'm doing my analysis, like I check, for instance, political ideology is one of my demographic variables, and check across conditions that to make sure, just to check that random assignment worked, and that I don't have, stacked a bunch of liberals in one group and a bunch of conservatives in another, just by crappy random chance. But if it wasn't for random assignment, if people were able to self-select into one group or the other, then, you couldn't necessarily make that assumption. Maybe it's that liberals wanted to be over in this group for a specific reason and conservatives were drawn to this other group for some other reason. And so, again, all you have to do here is regress that covariate on your factor, and if it's not significant, then at least you're good there. These two things are unrelated enough to not be a concern. So that wraps up this one. We're going to keep it nice and short and sweet this week. If you have any questions, just let me know.